So we are going to describe um, uh, some recent effort that we are focusing on the Share-VDE project, and specifically the usage of linked data fragments for our RES API layer. Prior to go deep into that topic, we need to describe Share-VDE, what is its domain model, and so on. So my name is Andrea Gazzarini. I'm a software engineer. I'm based in Italy, and in this context, I'm representing the Share-VDE initiative. I'm the Share-VDE lead architect. So what is Share-VDE? Share-VDE stands for Share Virtual Discovery Environment, and is a library driven initiative that brings together in a common discovery environment the catalogs, the bibliographic catalogs and authority files of a huge number of academic and national libraries from North America and Europe. Behind the system, behind the end user system, we have the what we call the knowledge base, what we call Sapientia, the Share-VDE knowledge base, where data is stored. So it's useful to understand how it is created. So we have several libraries, the participant libraries, universities that contribute with their data. In this stage, data is separated because each library, provides the data in a different, potentially in a different format, in a different way, through API, through batches, and so on. So we receive that data, and there is a part of there are kind of pre-processing where we execute several processes like deduplication, enrichment, clusterization, and we call this part clustering. It's not actual clustering, but okay, just to summarize, this is our clustering preprocessing, and the output of this set of components is what we call Sapientia, the Share-VDE knowledge base. Let's see how the data is organized within the Sapientia, the Share-VDE knowledge base. The domain model, the Share-VDE domain model, is basically inspired to the most popular BIBFRAME bibliographic framework from Library of Congress. So you will find a lot of similarities. At the same time, there are differences. So in the picture, we have the core hierarchy where, for example, the work entity has been split in Share-VDE between another entity called Opus and the work, which is basically the BIBFRAME work. The reason the reason about the difference is because we wanted to have a domain model more cohesive and how to say, tied to our context. Apart from the core hierarchy, we have also, as I told you, there are a lot of similarities. So, for example, the agent part is very similar to the BIBFRAME model. And we have subjects and what we call non-core entities like languages, genre, types, formats, places, availability, and so on. These are managed, all of these are managed as entities. So what we described the big picture, the overview, how the Share-VDE knowledge base is created, then how data is organized in terms of entities within the Share-VDE, the knowledge base, sorry, and then what about the single entity? We call it a prism. We refer to that term because uh, I'm going to explain. Let that let's assume that we have a library that uses uh, an ILS for creating for cataloging, and so it creates a bibliographic record. And this is the very first bibliographic record that is sent to Share-VDE. So a bibliographic record corresponds to a main entity, which is the instance that basically corresponds to the BIBFRAME instance. But other than that specific entity, in a bibliographic record, there are a lot of other entities. We have names, authors, publishers, places, dates, events, and so on. So the pre-processing components that I was talking does exactly that, separate those entities. And in the picture, in the example, the main triangle is the instance, is the entity that we create in Share-VDE that will contain the instance attributes taken from the bibliographic record, of course. But other than that, we have also a lot of other entities, authors, publishers, dates, events, and so on. These are the small triangles. So what happens if another participant provides a different bibliographic record for the same results, the same book, for example? Probably there will be a lot of intersections. And do we discard that data? No, absolutely. Because in the same way, the new bibliographic records will create other triangles, okay? So, for example, here's the triangle of the first library, Stanford, for example. This is the triangle, the instance triangle for the University of Pennsylvania, and so on, Alberta, and so on. The pre-processing components understands that all of those triangles belong to the same entity, an instance in this example. So it sums up everything, assigns to that group a URI, and forms a what we call the prism. We like this analogy because a Share-VDE entity is an aggregation of several things, but in any moment we are able to separate the phases. We always retain the provenance of each attribute in the knowledge base. So what about linked data fragments? So this is the big picture of Share-VDE. So starting from the left part, we have the several participants that contribute with their data in the way that we saw, and create the Share-VDE knowledge base. Let's forget the part on the right because it's about another topic. But basically, the Share-VDE knowledge base internally uses three kind of storages: an RDBMS, a relational database, a search engine, an inverted index-based search engine, and an RDF store. The first two are used by the API layer to provide GraphQL and REST API, GraphQL and REST access to our data. The third one, the RDF store, is what provides the RDF API, we say. So URI, the referencing, and the SpazioQL interface over HTTP, of course. In this talk, we are focusing on this part. So what the SpazioQL is the language, the standard de facto for querying an RDF store. So this is a very simple SpazioQL query that uses the core hierarchy. So objects, works, instances, items. And so SpazioQL, okay, is composed by a select part where the requester indicates what she wants to get back. In this case, a barcode, something called barcode, which is the barcode. And then we have a where clause that can be divided in several clauses called triple patterns. Why? Because they are composed by a subject, predicate, and object, and each of them could be a literal, an explicit value, a URI, or a literal, or a variable. The variable is used. The variables better are used for connecting one triple pattern with another. So basically, the where condition that controls the selection where I want to extract the information that I request in the select can be considered by as composed of a set of multiple triple patterns that can be potentially executed independently. Potentially, of course, is not always possible. The execution of a single pattern returns a partial view of the data of the entire result set. That partial view is called fragment, and since we are talking about linked data, a linked data fragment. So what are the participants of a linked data fragments architecture? We have clients, we have a layer that provides SpazioQL over HTTP. But actually, this is not executing any SpazioQL at all, because its purpose is to destructure the incoming SpazioQL into triple patterns, and each triple pattern is each triple pattern, the execution is delegated to a linked data fragment resolver or triple pattern resolver, a server that is in charge to resolve a single and simple request, a triple pattern request. And of course, this linked data fragment resolver needs to fetch the data somewhere. In Share-VDE, specifically, it fetches from RDBMS and from the search engine. So what is the advantage of such an architecture is that everything happens on the fly. If you noticed, we do not have any RDF store. So that means the SpazioQL layer needs to destructure the SpazioQL queries, make some potential optimization of the query, and delegate the execution of each triple pattern or triple patterns group to a specific server, a linked data fragment or triple pattern servers. Then the several response, then among its job, other than delegates, it then receives the fragments from the several servers that it contacted. And then those fragments are merged and the response is returned to the requester, to the client. This is a very lightweight architecture because the servers are very, very simple. They are supposed to receive a lot, probably, of requests, but very simple. For that reason, they are absolutely stateless, so we can scale up those linked data fragment resolvers as much as we want. And of course, we also need something scalable behind machines, because otherwise the storage would become a bottleneck, right? For that reason, we are within that prototype, we are migrating the RDBMS to a NoSQL database. So the underlying storage will be composed at the end by a NoSQL and an inverted index-based search engine. So coming back from the previous high-level architecture, with the introduction of linked data fragment, we are basically removed that part. We no longer need any RDF store. And that's the first point. No RDF storage. We have a distributed computation because we have a lot of replicated, simple triple pattern servers that are supposed to receive an important number of requests, but very, very simple, because a triple pattern request is a request where the service accepts a subject, a predicate, and an object, and potentially each of them could be a wildcard. Okay? The very good thing about this architecture is that everything happens at real time, at query time. So in the next couple of slides, we'll show you concretely what two benefits, for example, that we implemented. So we said that each entity is composed by the contribution of different provenances, right? So a client that wants to get back the representation of the resource associated with that URI, that's the same if I run a SparkQL query, of course. In this example, I'm just dereferencing a URI. So I want to get back the RDF representation of agents/201, okay? Using a HTTP header, but it could be everything that is included in the request, also query parameter, I can select the provenances that I want to get back in my results. So for example, here I want the RDF representation of agents 201, but only the contribution of the University of Pennsylvania, Alberta, and Chicago. And that's very easy because we know that the Share-VDE entity is a prism, but we are always able in any moment to destructure them. So it's just a matter of selecting the phases I'm interested in and return to the client the RDF created using those contributions. Another interesting thing is that what about the ontologies used for representing the data? is not fixed, because again, we do not store RDF anywhere. We store our data in an RDBMS, now in a NoSQL later, and in a search engine. So it has basically nothing to do with RDF. That means that a query client, we can transform and translate and create the RDF as we want. So in our prototype, we created a couple of mappings. One that uses BIBFRAME plus Wikidata ontology, and another XDC that is using XDC, XDF are codes that we assigned. That they mean nothing, basically. It could be whatever. And XDC that schema.org and Dublin core. So the same agent, the same request, basically, /agent/201 with a different HTTP header that says, give me the representation of the agents 201 using the XBF mapping. Okay. And so the client, the RDF API, sorry, would return something like this. This is an extract, of course. The same request with a different value for that header could provide a different representation of the same resource. Different because here we are using another two ontologies. The cool thing is that we can combine this example with the example above. So we could say, give me the agents 201 using the XBF mapping, but I want in the results only the contributions of libraries B, C, P, and F. Okay, so this is very powerful in our opinion, because again, everything happens in real time, and we no longer need an RDF store. And of course, there is a but. It depends on the but is related to the network latency, because you saw that the architecture is very, very distributed. So it depends basically on the kind of the data access pattern that your system is supposed to serve, right? And so I'm not saying, of course, that is the solution for everything. In our context, it seems to be very, very helpful, useful, and interesting. And so that was this last slide. Yuda, am I supposed to end at 10 to 4,
Yeah.
right?
Yeah. We're just about at time. If anyone, we could maybe do one question, but I didn't want to say the prism analogy was really interesting. And I think when you got to the slide where you're like, we don't need RDF anymore, I was like, for some people that's like really blasphemous, and for other people that's really practical. So I think you sort of demonstrated why, removing the RDF store is actually helping. But do folks have any questions? We have time maybe for one before we go on to the next speaker. None so far. Yeah, and I think we're at time. So I think that was a really in-depth explanation of that. And if people have questions, please follow up on the forum chat. So thank you so much, Andrea. That was really enlightening.
You're welcome.